Welcome back to Advanced Higher Mathematics, and today we're entering topic 2, which is differentiation 2, in which we will look at slightly more advanced methods of differentiation. Now 2.1 is going to be implicit differentiation. Very interesting in my opinion, and shows how important knowing the basics, in this instance the chain rule, is. So let's first of all look at what the word implicit means. To do this, we're going to start by considering its opposite, explicit. Now, something explicit also means in common English, for example, stating something in a way that cannot be misunderstood, right? If you explicitly state that you're going to school tomorrow, then it can be mistaken. So you would maybe say, I'm going to school tomorrow. But if you say it implicitly, you would maybe say, I'm going to go and learn tomorrow. That could maybe be an implicit way of saying you're going to school, without directly saying you're going to school. Now, functions is similar to this, and say we have a function y equals 2x squared minus 4x plus 2. Well, this is explicit, because it's directly saying what y is. It's directly saying, okay, well, y is equal to 2x squared minus 4x plus 2. Same with a function such as f of x is equal to 2 cosine of x, right? That's directly saying that f of x is equal to 2 cosine of x. So y is equal to 2 cosine of x. But what if we have something such as x squared plus 2xy plus y squared is equal to 12? Well, that's actually not explicit, because another way of thinking about it is the fact that the y's and the x's are mixed together, which is slightly problematic for what we know so far, because we can't separate the x's and the y's as we are so used to. We're so used to having just y equals something, and then we differentiate it. But here it's a bit less nicely laid out, and so we have to do extra work for it. So let's get into the method of doing it. And it's quite a hard concept to understand, but once you do understand and you have that moment when it just clicks for you, it's extremely satisfying to understand implicit differentiation, which is why it's one of my favorite parts of maths. Now, the thing to remember when doing implicit differentiation is that y is a function of x, okay? Y is a function of x, so it's dependent of x. And so, let's look at an example. Let's say we just isolate this, right, in the function. We just isolate the xy, okay? In fact, no, even simpler. We just isolate y squared. Well, by the chain rule, this actually needs the chain rule. If we want to find something, so dy over dx, if we're differentiating with respect to x, this is when this notation becomes better, much better, in more advanced differentiation. And derivative with respect to x, remember? We're finding a derivative with respect to x. So if y equals 2x squared, or just, 2x squared, then we're actually differentiating both sides with respect to x, right? This is equal to the derivative with respect to x of 2x squared. And now, we're not saying that the derivative with respect to x of y is just 1, or something like that. We're saying it's dy over dx, right? It's that simple. We can't really find it, so we're just going to call it dy over dx, and that's equal to 4x. So similarly here, we can't just say that this the derivative of this with respect to x is 2y, because that's the derivative with respect to y. And so, instead, we use the chain rule. And so the outside function, first of all, is x squared, and the inside function is y, because y is actually a function of x, so it's a function. U prime is 2x, and v prime is actually simply dy over dx, right? So it's actually, we're keeping it really simple for ourselves, so we're not trying to solve anything. We're just saying, well, of course, the derivative of anything, the derivative of, so say v was equal to 26 cosine of the square root of x squared, that's a bad example, of x cubed divided by tan inverse of cosine of x, right? This seems impossible to differentiate. In fact, it is quite difficult, not impossible. but it's still true to say that v prime is equal to d, then all of this in here, divided by dx, right? That's true, because we're just saying, basically, this is basically the question you would be being asked. Here we're just writing this as a question. We're not actually giving a fixed answer. And so now we can just simply apply the chain rule, which is going to tell us that the derivative of y squared with respect to x, right, is going to be equal to, with respect to x, so it's going to be u prime of v times v prime, which is just equal to 2 of v, so 2y times dy over dx. It's just that simple. And so sometimes we might be using product rule as well as this, but anytime you see a y like this in another function, it calls for implicit differentiation and using the chain rule. Now we'll look at a couple more isolated examples, and then we'll look at how to actually find the derivative of a whole function. So let's say we had xy, right? Just this on its own. Of course, by the way, if it's a function like, say, I don't know, 1 equals xy, then you can simply do y equals 1 over x, and then differentiate it like this. But now I just want to isolate parts on their own of functions. So xy here, we have, first of all, it might even seem like we just have this, the product rule, for which u is going to be x and v is going to be y. So u equals x, v equals y, so u prime is equal to 1, right? That's pretty simple, the derivative of x, but v prime is not equal to 1, it's equal to dy over dx. So the derivative of this, dxy over dx, is equal to u prime v plus uv prime, which is equal to 1 times v plus x dy over dx. So it's equal to y plus x dy over dx, right? So it's very interesting, really, and I hope you do enjoy it quite a lot. And now let's look at an actual problem involving this. We'll stay with a decently simple polynomial for now. So let's say we were given that x squared minus xy plus y squared is equal to 1, okay? This is our question, and then we're asked to find dy over dx. Oh no, we can't put y on its own. Aha, but I know how to do implicit differentiation, so it's all good. Alright, so I hope your reaction is similar to that when you see it in the exam. Maybe just don't say that out loud, or you might get kicked out of the exam hall. So anyways, this is quite simple because it's just broken down into separate parts like we've just seen. So the first step is to differentiate both sides with respect to x, because that's allowed, right? In algebra, you know how you're able to add something to both sides, multiply both sides by the same thing, divide both sides by the same thing, etc. Well, you're also allowed to differentiate both sides, and the equation remains true, which means that the derivative of x squared minus xy minus y squared with respect to x is equal to the derivative of 1 with respect to x, which is equal to 0. And this is equal, we can separate it by where the subtractions are. In fact, sorry, that's meant to be a plus. So that's equal to d over dx x squared minus d over dx xy plus d over dx y squared, and that's equal to 0. So let's break down chunk by chunk. D over dx of x squared is just 2x, right? That's just the power rule. Now xy we saw on the last page. You can try and do it yourself to make sure you remember. But xy we got is equal to y plus x dy over dx. X plus y dy over dx. So since it's all in brackets, it's actually minus, what did I say? Y I have already forgotten. Yeah, it would have been x, I assume. Minus, and that's meant to be y. Minus y minus x dy over dx. And then plus the derivative of y squared, which we saw applying our chain rule again here, is 2y dy over dx. 2y dy over dx, that's equal to 0. So, we're still not done though, there's still a couple more steps. First of all, we're going to add all the things which are independent of dy over dx to the other side. We'll get them on the other side to isolate this side. So we get that minus x dy over dx plus 2y dy over dx is equal to y minus 2x. And now the trick is we factor out the dy over dx. And now we get that dy over dx times 2y minus x is equal to y minus 2x. And so this means that dy over dx is equal to y minus 2x divided by 2y minus x. Oh, but there's y in the final answer. Well, that's fine. There's no rule saying we can't have y in the answer to our derivative. In fact, we need to have y in this case. We can't get rid of y. So maybe, in fact, we would have a further on question, which would ask what the tangent to the line, what the gradient of the tangent to the line at the point, let's say 2, 1, that's a very bad example, that's undefined, at the point 1, 2 is. So recall that the gradient of the tangent to a curve is just the derivative, right? So this is basically just saying what is the derivative of this function here at the point 1, 2 of dy with respect to x. And to do this, we simply plug in our values, right? This is y, this is x, so it's equal to, so dy over dx at point 1, 2 is equal to 2 minus 2 divided by, it doesn't really matter, of course, which is just equal to 0 because the numerator is 0. So that's an example problem, a relatively easy one, but still a problem. So let's look now at something with, for example, maybe a trigonometric expression. That might be a bit too long. I've got another side of paper here. It's quite a mess with all my paper. So let's say we had y is equal to cosine of x plus y squared x. So we can see this part is going to need implicit differentiation. Sorry, not y, in fact. Something like, let's say 12 equal to cos of x plus y squared x minus, let's see, minus, we'll say y cubed. Then what is dy over dx equal to? That could be a question that you're asked. So press pause and try and solve it yourself. Alright, I'll assume you've tried. So the first step is to take the derivative of both sides. So we get that 0 is equal to, so cosine of x, its derivative is just negative sine of x. Then y squared of x will need some work, so we're going to do it over here. So y squared x. So we've got u here, and we've got v here, and so we need to use a product rule, but we also need to use a chain rule. So u is equal to y squared, v is equal to x, so v prime is going to be equal to 1, and u prime. Now you can go for the chain rule, but you should be quite used to it just being sort of, way to think about it is the product rule, and then you multiply by the derivative. So it's equal to 2y dy over dx, but go through the steps here if you're uncomfortable with how this works. And so the derivative of y squared x is equal to u prime v plus uv prime, which is equal to 2y dy over dx times v, which is x, plus uv prime, which is y squared times 1. So this is going to be equal to 2yx dy over dx plus y squared. So we can write that in here, plus 2xy dy over dx plus y squared. And then y cubed, well, sort of the power rule thing again. It's going to be 3y squared dy over dx. I'm going to go over the steps just to make sure you're definitely comfortable with y to the power of something. So y to the cubed is actually just a function of a function, right? Our outer function is x cubed and our inner function is y, because y is actually a function. So u equals x cubed, v equals y, So u prime is equal to 3x squared, and v prime is just equal to dy over dx, because it's just a derivative, so we're just writing it as the derivative without exactly evaluating it. So the derivative is then u prime of v times v prime, which is equal to 3y squared times dy over dx, which is what we have here. So this is 0, but we want dy over dx on its own. Probably shouldn't have put this here. So imagine we go down to here now, from here. So first of all, we add anything that doesn't matter about dy over dx, which is this. So we'll add this to the side and subtract this from both sides. So we get that sine of x minus y squared is equal to 2xy dy over dx minus 3y squared dy over dx, which can be factorized. We can factor out dy over dx to get 2xy minus 3y squared. Now we divide both sides by this here, so we get the dy over dx is equal to quite a nasty one, sine of x minus y squared divided by 2xy minus 3y squared. So that's roughly all you need to be able to do for implicit differentiation. In fact, most of the time it's simply going to be basic polynomials. You'll rarely have, in fact, if ever, have any trigonometric functions of y. For example, you won't be asked to find the derivative of, say, tan inverse of y. If you are, then you're simply using the chain rule twice, which shouldn't be too much of a problem. So see you in the next video for, I believe if I've got my orders right, logarithmic differentiation.